just a little bit of introduction about my background so that you get a flavour for where I'm coming from. I did theoretical physics in TCD, like Connor said. I'm now in the Applied Physics Research Group, based here in CRANN in Igor Shvets's, he's my supervisor. And the main topics of my thesis is nanowires, and so the topics in there are magnetism, semiconductors, and fabrication. But I mean, this is about being a postgraduate student, so I'm going to try and keep it as general as I can. But everybody you talk to who's a postgraduate student is obviously going to have a very specialized field of research. So anyway, moving on. The motivation behind my work is I guess the advancement of hard drive storage and computer functionality. So this is a picture of a hard drive being loaded onto a plane in 1956. It's actually an IBM hard drive. I can't remember the name of it. It would have cost about $160,000 in today's money. It stores 4.4 megabytes, so it would hold about 4 minutes of MP3 music. So, oh, how things have changed. This is a picture I took off Amazon just before the talk started. You know what it is. It's a terabyte hard drive. It's about $70, and that just kind of shows the huge pace of achievement in terms of bringing the cost down and bringing the memory density upwards. A lot of these advances have been made in research institutions, just like CRANN above us. So that's the motivation for what I do. What I actually do is I grow these magnetic nanowires. So this is a height profile image. I guess the yellowy bits are the highest bits, and they correspond to where my nanowires are. And they're about 20 nanometers wide. That's about 80 atoms. And what I do is I measure their magnetic behavior, how they influence each other as a function of separation, how they behave at different temperatures, and so on. We can also grow nanodots, and we look at their optical properties. Again, these are silver nanodots. They might be useful for biosensing or sensing applications. That's why they're important. And recently I've been growing these gallium arsenide nanowires. So gallium arsenide is kind of like silicon. It was kind of expected to be the big semiconductor, but then silicon took over. But there are some nice applications of gallium arsenide, such as growing these nanowires. So I look at the different shapes that you can grow. And this is like a close-up atomic resolution image of one of the nanowires. You can see all these little white dots are the individual atoms. And I'm interested in this little band, this defect. We can zoom in on it and see where the atoms kind of behave differently in certain areas. So that's the kind of thing that I do in my day-to-day job. So day-to-day stuff, I don't think there's been an awful lot said about this in other talks, but I'm going to give you an idea of what you would expect to do in my job. It's typically regular hours, Monday to Friday, but you have to expect to work evenings and weekends from time to time because maybe equipment is only available then. Maybe you work in some kind of nuclear physics research where you have to man the beamline at certain times. So there's lots of different reasons why you might be needed to come in at evenings, maybe even nighttime. You might have to do an experiment that runs for 10 hours just because of the very nature of the experiment. So that's typical. This is a pie chart, very general about how I might spend my time. About a quarter of it making samples, that's fabricating. About a quarter of it measuring things. Reading, writing, arithmetic is just pretty much desk work where I have to read other people's papers, try and write my own, and do a little bit of theory. In the first 2 years of your PhD or your postgraduate, you can expect to do some coursework. In my case, it was about 6 hours a week. I also did some lab work of about 4 or 5 hours a week. You might have to do some correcting, some tutorials. And then miscellaneous stuff is like seminars, being trained on equipment, things like that. So this is going to vary very drastically from person to person. I guess if you're doing a theoretical postgraduate, the first 2 fabricating measurements are not even there at all. It's all desk work. And I guess reading is more so in the first few years and coursework. And then again at the end when you're writing your thesis, that's going to take most of your time. Flexibility is very important. Like I said, you need to be able to be available potentially at any time to do experiments. And so that's why just coming right out of your undergrad is a good time to do that because you don't have too many obligations outside of the lab. And ask people in your area of interest what they do. So this is just my pie chart. I'm sure there's lots of different pie charts out there. So ask other people in the area that you're interested in what they do, what their daily day looks like. So some advantages of being a postgraduate research student. It's interesting work. You're applying your brain all the time, so that's good. It's pretty satisfying to get nice data on the days that happens. There's good potential for future work. So you're picking up a lot of different skills. You're getting trained on different equipment. You're learning more and more about, in my case, semiconductors, I suppose. So I'd like to think that I'm kind of putting together a juicy CV for the big day when I get a real job. So there's good potential for travel or eventually working in a different country. Usually in research, you're studying something that is applicable all over the world. So it's not like being a doctor where you're licensed to work only in Ireland, or a lawyer where you only know about British law or something like that. I mean, from my point of view, electrons behave the same way in France as they do in South Africa, so that's good for me. I just got back this morning from a conference in San Francisco to present our work, and I got to go to conferences in Chicago and Atlanta presenting our work. We also get to use cool equipment. I want to keep talking about travel for a moment. I got to spend a year at the University of Notre Dame. The correct way to pronounce Notre Dame is the incorrect way, just so you know. So that's in Indiana, near Chicago, so I got to spend a year there as part of my research. So that's the kind of thing you can expect to do as well. On to cool equipment. This was our growth chamber over there. This is us in our, towards the back in these white bunny suits. That's to protect us from arsenite in the air. So that was a fun piece of equipment to use while I was there. This is a nice piece of equipment we have here in Trinity College. It's a helium-ion microscope. So it uses a beam of helium atoms to probe the surface so that you can find out what it looks like. And it's really cool. It's got incredible resolution, and it's what it doesn't do is it doesn't charge the surface. So it doesn't usually we'd use an electron beam, which damages the surface because you're applying charge to it. But this is a charge-neutral way of analyzing surfaces. So it's very suitable for using for studying biological samples, such as maybe cancerous cells, which is what it's very commonly used for. I use it for imaging gecko feet. Do you know what a gecko is? It's a lizard. They're able to walk on walls and across ceilings. And the reason they're able to do that is because they have this amazing network of hairs at the end of their scales on their toes. And it's really unusual amongst reptiles that they have hairy scales, but they do. And at the end of these hairs, they split out into these tinier hairs at the ends called setae, and this increases the surface area of their toes, so they're able to walk on walls and even on glass. And there's a scale bar on the bottom right. I'm not sure if you can see it. It's a micron, that little yay-wide bar. And a human hair is 70 microns wide. So a human hair would be, I guess, the width of this wall, maybe, yeah, about that wide. So it shows you the kind of level that we're working at. It's really the atomic level. And the equipment that we have to examine these kind of things is really world class. This is, it looks pretty similar, but this is actually a tarantula hair from a tarantula's toe. So this was done on the helium-ion microscope. And so I don't know, it's just one of the things that I've done on the side. Maybe one thing that I should have mentioned is that while you have to be flexible in time, you're also flexible in the work that you do. So there might be a project proposal written up that you've applied for and you take, but there might be more scope to wriggle around within that. So that's one of the nice things about being a postgraduate student. Some minor drawbacks. I guess it wouldn't be fair if I didn't mention some of the drawbacks as well as the advantages. The pay is not astronomical, shall we say, but it's enough to get by on. If you get funding, I guess typically most people in postgraduate study would be getting funding through ERCSET, and that's between 16,000 and 18,000 euro a year. Typically, a lot of the funding that we get is tax-free. It's enough to get by on. As you get older and grayer and wiser, like me, well, I don't know if I'm all of those things, but I don't know, it cashes into everything. Maybe your viewpoint will change as from being 18 years old to your 20s and 30s. Depending on your point of view and your level of success, life as a researcher might be a series of short-term contracts. So if you're looking for job stability, and if you're looking for, it really depends on what area you're in, but if job stability was really important to you, and you wanted to buy a house somewhere and stay in it for the next 60 years, research might not be the area for you. So skills that you would prefer to have for postgraduate study, you need to be self-motivated, so you need to be able to work on your own and to get up every day and do things without being prompted to do them. You need to be creative in your approach, because you have to come up with new things, otherwise there's no point. So it is a little bit artistic, actually. When you're in this area for long enough and you see somebody's other approach, you really admire the creativity in it. That's really what you admire most about other people's work, is that they thought of something new. You need to have good interpersonal skills. So it's different to being an undergraduate where you're responsible only for your own success. That's not like it is in the real world. You kind of sink or swim together. So you need to be able to work with your group, and that's really important. Good written and oral presentation skills. These are ultimately your products. I guess your research is really what you might think of your product, but people only know about your research if they're able to read about it or if they see you giving a talk. So it's important that you're pretty good at those. So any kind of final year or third year projects that build up your teamwork or your presentation skills, you should try and maximize your efforts at those, and that will suit you well. So you need to be a bit robust. There will be setbacks. Things will break. Parts might not arrive on time. You could be 3 months working at something that doesn't work out. But you need to be able to pick yourself up after these things and get on with it. So just a few snippets of advice, and this is again from my background, but hopefully they're useful to some people. Find an area that you're really interested in and start asking as many questions as you can of the graduate students in that area. All about what they do, what their daily schedule is, whether they work in the lab or at a desk. These might be important to you. Being able to work with your group and your advisor is the most important thing. So there might be a project proposal. I mean, you need to be interested in the area that the group is working in. But as you learn more and more about your area over the first 2 years, you can start to guide it and tailor it to suit your own, your own interests. Ask the people in the group about the funding availability. What funding are they on? And look for sources that are a little bit off the beaten track. There might be, sources of funding that other people might not have heard about, and there might be, a lower competitiveness for those. So keep an eye for those. My own funding is with, it's a Naughton Fellowship, so it's sponsored by the Naughton family, after which this building is named the Naughton Institute. And there wasn't as much attention on that as there might have been for ERCSET. So those things are really nice to find, and they can be really lucrative. So that's it. Thanks very much for your attention, and if you have any questions, I'll do my best to answer them.
What's the smallest thing you've looked at in your microscope?
I guess atomic level is as small as I have looked at, yeah.
Okay.
There are other tools that they have here. They have scanning tunneling microscopes for very regularly looking at surface atoms. And yeah, it's really amazing the kind of resolution that you can get in CRANN now.
Okay.
All right.
Excellent.
Thanks very much.